go. All right, here we are, collecting like terms, this lesson's called, and it's not clear what that title means. Like a lot of math lessons, the title comes up and says something, you're like, I don't know what that means. So it's interesting, titles in math lessons don't always explain what's happening. Good lesson today for you, because you get just to fill in the blanks here as we go along. Here's the big ideas. A blank is a letter used to represent an unknown number. A variable is the word we want here. Maybe you've seen that word before. Hopefully you have seen the word variable before. It's a perfect name, actually, if you really think about it. Variable. It means it varies. It depends. We don't really know what the number is going to be. It can be different numbers. We don't really know what's happening yet. And invaluable in any kind of mathematical endeavor is the ability to go, oh, we don't know what that is. We're going to calculate it later. And it's convenient to use letters to represent it. Example, x, y, a, or b. Well, there's nothing special about x or y or a or b. That's just when we're first learning about math, we often use those letters to get you started, and we use them often so that you get used to it. But every letter is used in math. In fact, we have to switch over to Greek letters in upper level math because we run out of letters to represent everything we want to work on. Okay. So you've seen the word variable before. You've seen the word variable before? Of course. So now it might be a little, the rest of this might be new. A term is a product or quotient of numbers and variables. Here's a bunch of terms. 3x is a term because it's two things multiplied together. It's 3 times x. Negative 5xy is a term because it's negative 5 times x times y. You got this group of little numbers multiplied or divided together. We call it a term. So negative 12a squared b is a term, and 7x squared y is a term. And at first glance, you might be like, well, how can I tell which ones are terms? Like, how can I separate the terms? But terms will always be separated by plus or minus. So here comes my highlighter. And if you're so excited about the mark you got in the first chapter, or you want things to improve, when I go to highlight, definitely highlight the things I highlight, because I try not to do it very often. I'm like, make sure it's a big deal when you highlight as the teacher, because it's really a message to everyone in the class that this is a really big moment. Even if you don't have a highlighter and you want to do it with a red pen, that's fine. If you don't have either of those things and you want to put little stars beside it, I used to teach someone who used to do that all the time. He'd have his little pen out and he'd just put these cute little stars beside it to let himself know, hey, big deal. And again, I'll try and keep to it where I don't do it very often so that when I do put that highlighter on there, you're like, oh, this is big. That doesn't mean it's difficult. It might be something really easy, but it's important. So, in algebraic expression, terms will be separated by plus or minus. That's how you count terms. That's how you know when you're moving on to a new term. 3x plus 2 has two terms because there's a plus between them. As soon as there's a plus or a minus between them, you know, oh, that's a new term. So 3x and 2. Immediately somebody says, well, isn't that second term positive 2? And this is one of the weird things about this lesson is we're really going to get to the bottom of this thing is that positive or is it add? And the answer is yes. That's positive and it's add. It just depends on what we're going to go do with it, whether we're going to think of it as positive or add. That's actually good news for you. Whichever way it's better for you to think about it in the question you're doing, that's the way you can think about it. So positive and add is sort of interchangeable. Asking if this is positive or add is a little like asking me, Mr. Todd, are you a parent or a teacher? I'm like, yeah. Right now, I'm mostly teacher. As soon as the bell goes, I'm mostly parent. But I can switch back and forth between the roles. If I get a crazy text message in just a second that one of my kids is sick, well, suddenly I'll become a parent again. You know, so it's just whatever's convenient. That may seem weird at first, but you'll see when we go to do the questions, it'll only help us. We'll be able to go, oh, I'll just think of that as negative. No problem. Next, negative 5xy minus 4x plus 10y. There's the little separators, the negative and the positive. So this has three terms. It has negative 5xy. It has 4x. And it has 10y. And again, the immediate question that comes up is, wait a minute, isn't that negative 4x? Is that a negative 4x? Or is it subtract 4x? And the answer is, yeah, whichever you need it to be, whatever makes sense for you. So if someone wrote 4x as the middle term, I'd go, yeah. If someone wrote negative 4x, I'd go, oh yeah. You can think of it that way. If that's bothering you, it should. But by the end of the lesson, you'll go, oh, I see how you decide. There's times when it's like, you want to do it this, I'll give it away. If it's the first of that type of term, it's a negative. If it's in the middle somewhere, it's better as subtract. You'll see later. So there is a guideline here on how to handle this. A blank is a term that does not have a variable. Okay, so you can have terms that don't have variables in them, and we call them constants. A constant. It means it doesn't vary. It's actually pretty good words. Sometimes in math we use words that's like, where are you getting these words from? But today's words are pretty good if you really think about them. Variable. It can be different things. Constant. It can't be different things. It's the same thing all the time. So in the expression 5x plus 4, the constant term is the 4. See, 4 doesn't change. No matter what happens, 4 is going to be 4. Whereas 5x might vary. It depends what x is. If x is 2, 5x is 10. If x is 10, 5x is 50. See, it varies, and that's why it's called a variable. It changes based on what x is. In the expression negative 12x minus 5y plus 3y, the constant term is 5. Or is it negative 5? Yeah, it's 5 or negative 5, or maybe you subtract 5. So if you put a negative there, I'm with you. I totally get what you're saying. Yeah, so more later. The blank is the number part. Maybe you've seen this word before. They usually do this word in elementary. Coefficient. That's a less explanatory word. That word isn't as obvious. It's just a word you have to know. And here, negative 5x squared y has a coefficient of negative 5. But I'm curious, is most of that covered in elementary school? Part of it covered in elementary school? None of it covered in elementary school. Yeah, you see, I see every answer. So no matter where you're at, don't worry. I'm teaching it like you've never seen it before. And if you have, well, you can be bored and find it easy, I guess, until we get rolling here. I promise by the end of the day I'll do some stuff you didn't see in elementary school. So yeah, we'll get there. Questions on this page, though? More time? Who needs more time? So blank as any expression involving the sum or difference of terms. It's called a polynomial. So anytime we have an algebraic expression that has things added or subtracted together, we call it polynomial. Now, I'm going to do a little side note here. Poly means any number. So when you see poly in front of something, that's a prefix meaning, any number of terms that you want. There's specific polynomials, though. If you have one term, you get monomial. Mono might be a prefix you've seen before. It means single, one. If you get two terms, we call it a binomial. Like bicycle means two. And then three terms, we call it trinomial, like tricycle. All right, well, if you came in today sort of half awake, which happens, and you're just shaking the cobwebs out from the morning, now's where you might want to listen. There's a lot in this lesson that as soon as I explain it, you go, okay, I get it. It's a lot of terminology and so on. But this particular concept is a little bit tricky. So you might want your full brain power for this one. The degree of a term is the sum of the exponents of the variables. So when you're looking at a degree of a term, I'm just going to highlight that word. Degree of a term is the sum of the exponents of the variables. So when you have trouble with this later, and most people do, the first time through this, most people have a little bit of trouble with this. Just go back to this definition. It means you add up the exponents of the variables. So I'm going to go down to this one. The degree of 2x squared y is add up the exponents of the variables. X squared has exponent 2. Y has exponent 1. If you're ever confused in this chapter about single letters like that, go ahead and write a 1 on top of them like that to go, okay, just when I go to do this question, I'm going to think of that as a 1. So here, the degree is 3. I've added up all the exponents on the variables. Just on the variables, not on the coefficient. Gee, we're up to something with this degree. The degree really tells you how many dimensions, how many degrees, how deep this term is. And there's some big ideas coming from that, but we don't go too much farther with it in grade 9. We just introduce the idea. Now, the degree of a polynomial is a little different. I'm going to switch over to my red highlighter, because this, when I go to red, I'm like, you really got to read this to make sure you got it down pat. It says the greatest degree of its terms. So, this one's a polynomial with 3 different terms. And the game is, find out which one has the highest degree. So this first one, we already did the first one, it has degree 3. What about this one? Think about it to yourself. Just this term, 4ax squared y cubed. Think to yourself, what degree will that one have? Just this term. So I'm going to add up the 3, the 2, and whatever exponents on a. Just that term. 6. That has degree 6 because it's 3 and 2 and 1. How about this one, 18xy? It's so easy, it's hard. 2. And so when I'm doing a whole polynomial like this, the game is find the highest degree. You're looking for the biggest one. And the biggest one here is 6. So 2 different ideas in 2 sentences. 1, degree of a term, where you just add up the exponents to the variables. And then degree of a polynomial, you got to do them all and find out which one had the biggest. How's that the first time through? Is it okay? Few nods. Okay, geez, this was much easier. It took me all week to get my grade 12s to nod or shake their head. They just want to sit there and have me pour information into their brain. They don't want to have to respond. But the nods and the shaking heads really help me. And if somewhere along the way it's like, no, I don't really get it, the tiniest little shake and I'll go. Or you can go with frown. Totally frown at me and I'll be like, okay, re-explain that. It's best to learn it right in this moment as opposed to later. More time here. Is the fill-in note fun? Yeah, saves you a lot of effort, yeah. I'll do that one. See, I really think about it before I lesson. I really think, is it best that they write it all down? Or is it best that they listen? And I try and do what's best for your learning, not what's best for my photocopying, because I don't care about that at all. Okay. Oh, this is important. This is not difficult, but this is the important part of the lesson. I know I got really locked in here and highlighter, and I said this was the difficult part of the lesson. This is now we're on to the important part of the lesson. Like terms have the same variables with the same exponents. And I know I said I'd use the highlighter sparingly, but that has got to get the yellow highlighter. That's the whole lesson right there. I mean, literally, what was the title of the lesson? Collecting like terms. We're right into the lesson now. Like terms have the same variables with the same exponents. Unlike terms have different variables or the same variables with different exponents. The unlike term definition is troublesome. It's just a pain. Stick to the like term one. Like terms, same variables with the same exponents all the way through. It has to be exact same letters, and those letters have to have the same exponents on them. Example, 2x and negative x are like terms. They have the same variable, x, and x has the same exponent on it, 1. 6a squared b and negative 18ba squared. Are those like terms or unlike terms? I stick to what I said. I won't call on you, even if I make eye contact. Sometimes I look right at somebody and see if they'll put their hand up. But you don't have to. You can go the whole quadmaster and not answer if you want. But in a situation like this, at least try to answer it in your own head. I give this little delay. Answer it in your own head so you know whether you got the right idea or not. And then listen to the answers that come up. Are they like or unlike? They are like. She's so correct. This one tries to fool you, right? But if you look, this one has a with a 2. This one has a with a 2. The a's are the same. This one has b with no exponent. Well, exponent 1. This one has b with exponent 1. So they do have the same variables with the same exponent. But I got to tell you, no mathematician past about grade 9 ever writes things in this order. It might come up like that, negative 18ba squared. We always write them in alphabetical order. It's not a rule. It is not a rule in math that you have to write them in alphabetical order. It's just something all mathematicians do to make sure they don't get confused. So if you ever get this situation where your math textbook tries to fool you and does them not in alphabetical order, just stop and go, hold on, and just write underneath. Put them in alphabetical order. It's much easier management. 4 and negative 12 are like terms because they have the same variables. None. And this is the line I want to give away the big idea of the lesson. Here's the big idea right here. The idea of like terms is that they can be added together. If they're the same type of stuff, they can be added together. 4 and negative 12 could be added together. But you can't add 4 and x because they're not the same type of stuff. Like terms is all about finding the same kind of stuff. 2ac, negative 6bc. Like or unlike? Do they have the same variables? They got c's, but this one's got a and this one's got b. All right, so good. Unlike. Got to have the exact same letters with the exact same variables. And here's the one that really fools people. Negative 2x squared y and 16x squared y squared. Unlike, he says. He's right. But now I'm going to try and fool him, okay? They both have x's and y's. How can they be unlike if they both have x's and y's? Yeah, this one has exponent 1. This one has exponent 2. They have to be exactly the same. The rules about why they have to be exactly the same take a little bit longer to understand why it's important they're exactly the same. For now, it's like apples and oranges. They have to be the same type of stuff if you're going to add them together. Okay? Questions there? More time? To simplify an expression is to find an equivalent, simpler, and shorter expression. The expression 300 plus 4x plus 100 plus 2x is simplified to. Okay. Here's what you're going to be asked to be able to do, is to look at something like this and go, I've got 300, and I got 4 x's. I don't know what x's is. X might be 10. X might be 50. X might be 1,000. Whatever it is, they haven't told me yet. So when I look at this expression, I can go, well, I don't know what x is, but I do know that 300 plus 100 is 400. So you see, I've simplified things. Instead of having 2 different numbers in there, I just have 1 number. And the next part's the big deal for the lesson. Positive 4x plus 2x. I don't know what x is, but I do know I have 4 of them over here, and I have 2 of them over there, so now I can simplify things. I don't need them in separate terms. I can put them all together and make 1 term. What would the 1 term be if I had 4 x's and then 2 more x's? Yeah, you don't even have to know what x is to be able to do that. Sometimes when people are having trouble, I call them xylophones, which isn't a perfect analogy because x is a number, not a thing like a xylophone. But it helps to think this through, is to go, oh, 4 xylophones and 2 xylophones is 6 xylophones. I can do that simplification without even really knowing what a xylophone is. And that analogy is not bad. It's not perfect, but it's not bad. Notice, though, that in that, I did what I said would happen earlier. When I first read this, I said 300 plus 4x. Then later on, when I wanted to combine it with the 2x, I thought, oh, that's positive 4x plus 2x. You see how it's nice and versatile. You're like, you want it to be adding when you need it to be adding? Great. You want it to be positive because that makes sense for what I'm doing? That's great, too. So adding and positive are interchangeable. Subtracting and negative are interchangeable. How about this one? 400 plus 5x minus 100. This underlining trick is where it's at. It's the best thing I'm going to show you today is you go, okay, find the like terms. 400, subtract 100. I can put those together. 400 subtract 100 is 300. Positive 5 xylophones. Subtract a xylophone. How many? Subtract x. How many x's are we talking about here? Yeah, because that's a 1, right? So now I get positive 4x. And again, this positive, negative, adding, subtracting thing has happened in the middle of all this. When I read it at first, I said 400 plus 5x. When I went to put these x's together, I thought of that as positive 5x, not add 5x. So it's interchangeable. It's whatever you want it to be. I'm exaggerating a little bit. There's times when you're stuck with either negative or adding. But in these type of questions, that thing is completely interchangeable. You can think of it this way. Only like terms can be simplified. Geez, I said I'd behave with the highlighter and only highlight really important stuff, but this lesson has so many great sentences in it. I'm going to go highlight again. When adding or subtracting polynomials, only like terms can be simplified. You can't combine things that aren't the same type of stuff. And this example really helps to understand. If you have 4 cows plus 3 boys, you wouldn't then say you have 7 cowboys. You don't combine things like that. They have to be the same stuff. You can add cows with cows and boys with boys, but not cows with boys to get cowboys. It's not a perfect analogy, but it's sort of like this. You can't go 4C plus 3B and get 7BC. That's not a thing in math. They have to be the same stuff. Same variables, same exponents on those variables. So, the variables are used to sort the terms. The coefficients are used to count them. So, in math, this line would say 6t plus 7p plus 3t minus 2p. This is so good an example right before Thanksgiving here, right? Coming up. Turkey, ham, But if you were to count up, if you're a farmer and you're counting up what you had, you wouldn't combine turkeys with pigs. You'd say, oh, 6 turkeys and 3 turkeys, that's 9 turkeys. 7 pigs, subtract 2 pigs, that's 5 pigs. You put the same type of stuff together. That's why we need the same variables with the same exponents. Same type of stuff. Questions? The rest of this lesson is now I'm going to do some examples and try and use all that stuff in tougher and tougher examples and get you ready for your homework, which is attached. It's not in the textbook for this section. If you flip ahead in your little booklet there, you'll find at some point, I'm going to do examples for a while, and at some point it switches over after question 6. No, after question 7. Keep going. After question 8, I do up to question 8 with you. Then your homework starts after that. That's all attached there. Good? Your textbook doesn't do this concept particularly well, so we grab some stuff from another book. Okay. When simplifying polynomials, here's the 2 steps. Group the like terms and simplify like terms by adding the coefficients. So I'm going to do A with you here. And like we saw with exponents, you'll find your own shortcuts when you get really good at this. For now, I'm going to show all the steps. I'm teaching towards someone who hasn't seen this before or is having trouble with it a little bit. The first thing to do is underline the like terms. So there's negative 5x. There's its like term, negative 2x. And I suggest when you're first doing them, actually group them together. So I'd write, okay, so negative 5x goes with negative 2x. I'll write them side by side. I'm grouping them together. I'm collecting them up and saying, okay, these 2 things I can combine because they're the same type of stuff. I also have positive 7 subtract 3. So in that step, some people would argue I haven't done anything except put the terms together that can go together. After that, I just simplify by adding the numerical coefficients. In this case, subtract. Negative 5 subtract 2. Now, I need to warn you. If by the end of chapter 1 you're really good at mental math and you could do negative 5 minus 2, all the positives and negatives in your head, and you're so good at it, in the middle of all this, exponents, collecting like terms, all these rules, you might suddenly not get very good at doing that. You might want to lean on your calculator a little more this chapter while these concepts sink in. I give you all that time to think about negative 5 minus 2. What is negative 5? Subtract 2. You're nervous. I scared you off. Positive 7. Okay, so this is exactly what I was talking about. The 7 is so right. Let's talk about the negatives for a second, because in the middle of all this, we went through a whole chapter of positives, negatives, common denominators, multiplying things, then exponent laws, 1, 2, 3, 4, 5 exponent laws. Right now you got all these balls up in the air. Oh, it worked out perfect. I killed some time, and now our hand's back up again. I'm going to come right back to you. And all these things, and all of a sudden it's easy for one ball to just go like this, and you're like, oh, I forgot about the rules for subtracting, what is it? Negative 7. Probably what happened is she went, oh, 2 negatives makes a positive, and that's true. When did 2 negatives make a positive? Multiplication and division, yeah, but not for adding, subtracting. Good. So that's exactly what I predicted in this chapter. Just lean on your calculator just a little more until you get control of all these balls that you have in the air. Positive 7, subtract 3, that's positive 4. And again, you see this add sign, it was add 7, then when I went to put it together with this, I thought of it as positive 7. Okay? Notice this underlining. This is the number one mistake on these things. See when I underline the negative 2x, the negative goes with it. Whatever sign's in front of it goes with it. Okay? Here's B. 4y squared plus 3y minus 2 minus 3y squared plus 2y minus 5. I'm going to try and do the exact same steps, the same procedure. Step 1, underline like terms. 4y squared, what's the other like term in the list? 3y squared, and the little mention I did in the last example was take whatever sign's in front of it with it. So that's 4y squared, subtract 3y squared. This is the step that some of you, it won't take long before you'll want to skip this step. You're like, I can jump now. 4y squared minus 3y squared, I know what to do. And I give you permission to do that. But on the board, I want to show all the steps. Then, I got 3 types of terms this time. So I'm going to use my special underlining, my lightning underlining. Positive 3y. Is there another like term on the list to go with positive 3y? Positive 2y. And I do my lightning underlining, but look, I underline what was in front as well. So it's positive 3y plus 2y. I don't underline the last ones. I underline them by not underlining them, but you can underline the last ones. Some people love using highlighters here, and they highlight all the stuff that goes together. You can do that as well. The underlining is just a little faster than getting your highlighter out every time. Then combine what you have. 4 yam squareds. Sometimes it's fun to put a little label on them because it helps you visualize what might be going on. I don't know what a yam squared is. I don't know what you do. You take a yam and... I don't even know what a yam is, actually, when I think about it. Is yam like a potato, sort of? Anybody know what a yam is? This isn't a yam crowd. All right. 4 yam... You've heard of yams, though, at least? Yeah, okay. 4 yam squares, whatever that is, and somebody ate 3 of the yam squares. Subtract 3 of the yam squares. How many yam squares am I going to have when that's over? 1 yam squared. I don't even know what yam squared is, but it's a perfect analogy. I don't know what y squared is. They didn't tell me what y was, so I certainly don't know what y squared is. I don't know what it is, but I can still count up how many there is. You don't have to write the 1 out there. You could just write y squared, but I wrote the 1 there because it certainly helps the first time through. Absolutely. This one, positive 3 yams. These aren't yam squareds now. Yeah, the yam squareds are all done. These are just yams. Apparently that's something different. 3 yams plus 2 yams. 5 yams. If you're confused about the yam and yam squared thing, for a second, let's just think about what y could be. Let's just pretend for a second that y is 10. These are combining tens. These are combining hundreds. That's why they're different. They can't be put together because they're different things. If y's 7, these are 7s, and these are 49s. So that's why they can't be put together. And until we know what y is, we can't do any better than that. Then minus 2 minus 5, oh, big trouble. Again, I encourage you, grab your calculator on these during this chapter, because this kind of stuff, in the middle of everything else, your brain's going to be working on everything else. Good luck with that. You know, it's going to be a bit of a problem. Negative 7. Negative 2, subtract 5, negative 7. Good? I put those last two terms together. Any questions? Oh, your break's not till 10:15. Oh, we'll make it. All right. Complete the following chart by identifying the coefficient. So this is now the examples. This is the lesson is basically over, but I want to do some examples to really make sure all this stuff is clear. What would the numerical coefficient be in negative 6x squared y? Now this is where the lesson, a couple of people yesterday suggested looking back on the lesson. It wasn't because I didn't want to answer their questions. It's just when after a note is finished like that, you might be surprised how much power you have if you're just willing to use the note a little bit. It says numerical coefficient. You can go back to your note and look up what a coefficient was. The coefficient is the number part containing variables. So then I go back to here and I go, what's the number part? Negative 6. What's the number part? 12. What's the number part? Negative 35. You see? You see how good the note is. On purpose, as teachers, we try to give you as much information as we can about the lesson. So then look back when you have trouble in the homework, look back in those notes to check them out. Or call me over, but if you're at home or something like that, the note is your helper. Okay, where was I? Negative 6, that was pretty easy. 12, that was pretty easy. Negative 35, that was easy. What's the coefficient on this one? So easy, it's hard. If it was 0, thered be nothing there, right? So that's what's weird about this. It's such a mistake we make when we're first teaching math. Let's go back to this previous example. Here I got 4y minus 3y, and I got 1y squared. And I said, oh, you can write it like that. But I could have wrote it like this. When we don't write that coefficient out there, what we really mean is, oh, there's one of them. And it's a weird little math shortcut, and it sort of messes people up when they're first doing these things, because you're like, why wouldn't you just write the 1 out there? And I suggest in grade 9 that you go ahead and write the 1 out there. Anytime you run into an expression like that with x squared, is go ahead and write 1 out front, because it'll take away any confusion about the whole situation. So the coefficient here is 1. And weirdly, this coefficient here is 5, just the numerical part. It says, don't worry about the variable part. And I'm like, I wasn't worried about the variable part. There was no variable part. Okay, next question. Complete the following chart. How many terms? Oh, can you remember? You can flip back if you want, but can you remember how to decide how many terms there was? What was it that helped you count the terms? Yeah, plus and minus divides up the terms. That is, this minus says, oh, I'm starting a new term. This plus says, oh, I'm starting a new term. And that means this first one has 3 terms. How many terms does the second one have? 2 terms. And how many terms does that last one have? 1. Oh, type. Do you remember the names? 3 terms. What was the name of that when it had 3 terms? Trinomial, like tricycle. Ooh, my pen is being difficult today. How about 2 terms? Binomial. Those 2 are pretty easy because of tricycle and bicycle, right? This one not so easy. We don't need the prefix for 1 quite as often. Monomial. I got to be honest. knowing those common names is not as important as being able to collect the like terms. But it does come up where you have to know those three names every once in a while. Okay, degree of the polynomial. I want to do the last one first, because that one will be the easiest one to remember how to do it. How do we get the degree of the polynomial? Again, have trouble with this after the lesson's over, you just rewind back, find the part in the lesson that showed it, and review it. And in the case of these videos, you can just go and rewatch the video and rewatch the explanation. Add the exponents. So this one has 3 and a 1, so its degree is 4. It was also the degree of the term. So what's different when you have to find the degree of the polynomial when you've got several terms? Which degree do you take? The greatest one. So this one was 6 and this one was 1, so the highest degree there was 6. How about the top one? What's the greatest degree you see in the top polynomial there? Two. Next question, identify the constant term. Oh, what's constant term? What does that mean when we're talking about a constant term? Yeah, the one that doesn't have a variable, this constant term. And in this case, it's negative 10. I would take the answer 10, by the way. If you wrote positive 10, I'd be like, yeah, I get what you're saying. This isn't negative 10, it's subtract 10. Somebody else goes, no, that's negative 10. Until I know what I'm doing, that's negative 10. Right, yeah, you're both right. It really depends on what happens next, whether that's going to be a negative 10 or a subtract 10. So I just take both answers. I don't care. Questions there? More time? Are 6a and negative 4a like terms? Yeah. They have the identical. I even upgraded my word. I didn't just say same, I said identical variable part. The variable part has to be the same. How about 10 ABC, negative 12 BCA, and 5 CAB? Okay, I suggest from here on in math, when they ask questions like this, don't even hesitate. Fix what they did there and be a better mathematician than what they are. What should they have done just to make sure there's no issues here? Put the letters in alphabetical order. So just write it underneath. Negative 12 ABC, 5 ABC, and that really helps to say, yes, these are like terms. And I'm going to write the whole sentence again. They have the identical variable part. How about 10x squared y and 5x squared y squared? Are those two things like terms? No, not this time. They have the same letters, but the y and y squared are different. Why is that a big deal? Because y and y squared are different. Imagine if y is 10. 10 and 100 are different. You can't be adding them together until we know what they are. See, I can add 10 and 100. I'm like, I know. Until we know what they are, you can't, though. They're not the same exact things. I'm watching my watch. I want to make sure I'm done by your break. Questions there? Okay. I've had better luck the last couple of years with this, teaching it a little faster so that you can see the procedure. So if you have individual problems with the questions, let me know. But I'm going to go fairly quickly with these, and not because I think it should be that fast, but I want you to see it's the same steps every time. I really want to get through to you about the steps involved here. The steps involved are underline everything that's a like term. 5x minus 7x and plus 3x. Those are all like terms. In this first question, they're all like terms. After you've decided what like terms are, you just add them all together. 5 minus 7 plus 3. And again, I encourage you, lean on your calculator on these ones, because the mental math might slip away from you in the middle of doing all this other stuff. 5 minus 7 is negative 2, plus 3 is 1. So you can write 1x, or you can just write x. And I'm going to write both this time. Hi, welcome. Thank you. Here, we're in the middle of this right here. We're on this example right here. And we've been talking a lot about it, but for now, pick it up, whichever one you get settled for, pick it up from copying right there. And then I'll replay the slideshow for you during the next session so you can get it all down. Okay, here's the procedure. Step 1, it's the same every time. Step 1, underline like terms. See, 6a and 2a are the same stuff. I go 6a goes with 2a. New kind of underlining. I like lightning underlining, but you can do whatever underlining you want. Negative 5b goes with positive 3b. After you've collected them up and put them together, you just add them. 6 and 2, 8a. Negative 5 plus 3, negative 2b. And I'm going quickly on purpose because I want you to see the steps are the same every time. You'll get used to how to handle the different types of terms, but the steps are the same every time. Step 1, underline the like terms. 3x squared and subtract x squared, or a negative x squared, are the exact same types. They're both x squareds. So I write them together. 3x squared minus x squared. Get out my fancy lightning writing, underlining. Positive x goes with positive 2x. And then just add together the like terms. 3 xylophone squareds. I don't know what an xylophone squared is. Giant xylophone that's squared. But if I take away, how many is this? Take away, it says negative x squared. What number do we mean? 1. Yeah, and I encourage you. Write those ones in there if you want. There's another one right there. It helps in your thinking. 3 minus 1, 2x squareds. 1x and 2x, 3x. Same steps every time. Underline, collect, add or subtract. Me doing it fast, it may seem like I'm implying it's easy. No, I'm not trying to imply they're easy. I'm trying to imply that the steps are the same every time. Step 1, underline the like terms. Write them together. 4m and 2m. Lightning writing for the next type. Negative 2n minus 5n. Then add or subtract the individual pieces. 4 mangoes and 2 mangoes. 6 mangoes. Negative 2 nectarines. I don't know what that means. But then I subtract 5 more nectarines. Negative 2 minus 5 more, all the way down to negative 7. But again, relying on your calculator, going negative 2 minus 5. You don't need a n button on your calculator to go negative 2n minus 5n. You don't need it. Same as if I said, add 7 turkeys and 3 turkeys. You wouldn't say, where's my turkey button on the calculator? You go, okay, I know it's turkeys. I'll do the 7 plus 3. Same here. I know it's n's. I'll do the negative 2 minus 5. Same steps every time. That's the part I want to get through to you about, is the repetitiveness of these. Underline the like terms and write them together. 6x squared minus x squared. Lightning writing. Positive 3xy. Is there another xy term in there? Yeah. What? What are we doing here? What the heck? That is a negative 4xy. I'll fix it on this line. Silly of them to write it not in alphabetical order. It's not a rule. You can write yx if you want. It's just why would you do it? And then negative 3y squared plus 5y squared. When I'm doing these, I don't underline the last one because I can see by it not being underlined, it's sort of underlined. I can see what it is. So, and then 6 minus 8, negative 2x squared. 3 minus 4, negative xy. And then negative 3 plus 5 plus 2y squared. Maybe you like a 1 there. instead of just negative xy, but you'll get used to the negative xy. Well, we're going to have to break this into two parts. Okay, so I'm going to change the plan for today. I'm going to teach up until the break. We'll do the last of the lesson after the break, and then you have up to the break, up to lunch break, to work on the homework that's attached to this. Then after lunch, I'll teach another lesson, and then we'll see where we're at. We'll take it as it goes. Knowing that, let's slow this down. What's step one? Now that I've done a bunch of them, where hopefully you go, okay, I think I've got this a little bit better now. What's step one? 4a squared and negative 3a squared. Take what's in front. Yeah, take that negative up front. And I say write them together. If you're like, no, I got it. I so get what you're doing now. I don't need to write the separate line. I don't need to collect them up like that and write them out. That's fine. Negative 4a. Is there a like term with negative 4a? Yes, but take what's in front. Always take that what's in front. Yeah. So negative 4a minus 2a. And again, I don't underline the last two because I can see what they are. And then I get 4 minus 3, which is 1a squared. Negative 4a minus 2a is negative 6a. And 7 and 5 is 12. After you've collected up the like terms, then you can literally put them together. Find out what the total number is. And your calculator can be so much help there. What questions do you have in general, though? I'm not trying to imply this is easy. I'm not. What I'm trying to imply is there's a definite set of steps. Collect them up. Then subtract or add the individual terms. More time here? Okay, listen. The next two problems are meant to sort of, we don't do a great job of it, but sort of highlight why we're doing this. After a whole page of this kind of algebra, it's like, what is this for? Why would anyone do any of this stuff, really? And the next couple of examples give you a taste of it, a little bit of a flavor for why we want variables, okay? It's not perfect. The examples are not difficult enough that we would actually use variables for these questions. We'll practice on nice, easy ones, getting ready for tougher problems. Maggie earns $5 an hour when she babysits one child. So if she goes to her neighbor's house and they only have one kid at home, she gets $5 an hour. She earns $8 an hour when she babysits 4 children. When all 4 kids are there, instead of $5 an hour, she gets $8 an hour. I see some frowns like, I would never babysit 4 kids ever, first of all. That would never happen, let alone for $8 an hour. That's insane. This example was made up a long time ago when these were decent wages. Let x represent the number of hours she babysits one child, and let y represent the number of hours she babysits 4 child. Write an expression to represent her total earnings. Okay, this is really hard to get in the frame of mind of what they're doing here. So I'm going to try and get you there. Let's just talk about the $5 an hour. What would you type in your calculator if she ended up working 2 hours? Literally, don't tell me the final answer. Tell me what you would type in your calculator if she worked 2 hours. 5 times 2. Okay, what if she worked 7 hours? 5 times 7. What if she worked 11 hours? 5 times 11. What if she worked 99 hours? 5 times 99. You just go 5 times whatever the number of hours are. But in this case, it's X hours. We don't know how many hours. So we write down 5x. We say, oh, once you know x, we don't know x yet, but once you do know x, just multiply it by 5. Hopefully you kind of go, okay, I kind of get what you're saying here. Now, I'm going to do the same thing with babysitting 4 children. She's making $8 an hour. Let's say she babysits for 2 hours. What would you do? She makes $8 an hour for 2 hours. 8 times 2. What if she works 9 hours? 8 times 9. What if she works 99 hours? 8 times 99. But she worked y hours. So we go, oh, plus 8y. It says, once you know how many hours, You fill it in here and you go 5 times, you do that substitution from last chapter, right? You go 5 times however many hours. And this is plus 8 times however many hours. So the x and y is where you plug in the number of hours. If you want, that's what this expression is. It's a plug-in thing where you can just plug in number of hours. How's that example? First time through, it's supposed to be like, on a scale of 1 to 10, it's supposed to be 5 or more. You're supposed to be like, I kind of get it. But it's weird switching over from numbers to variables. Questions here? More time? Okay, so you're on your break till 10:20. I'm going to start teaching again at 10:25 and finish up those last few examples, okay?